All right. Well, now let's turn and talk about central force problems in quantum mechanics. Hang on. Okay. In a central force problem, the potential energy is spherically symmetric. What that means is that the potential energy, which in principle um, might depend on position in any possible way, is a function only of the distance from the origin, like this. These problems are really interesting because there are many problems that behave like central force problems, one of them being the hydrogen atom. Okay? But what's interesting about central force problems is that because the potential energy only depends on distance from the origin, but not on the angle, it means that it means that there are no forces that act on particles in the tangential directions, in the angular directions. And because of that, the angular momentum of a particle is conserved. Okay? So in central force problems, angular momentum is conserved. Okay? Now, it might be obvious, but central force problems should naturally be treated in spherical polar coordinates. Okay? That is, we're going to go from coordinates x, y, and z to coordinates r, theta, and phi. Okay? And, well, you probably remember how this works. I'll just sketch it out to remind us. Starting with a coordinate system like this one here, now we're going to label points in space using r, theta, and phi, where if this is my point, then r is the distance from the origin. Theta is the polar angle, which in physics we draw from the z-axis. And finally, phi is the azimuthal angle, and we can find that by dropping a perpendicular down to the xy plane and drawing a vector out from the origin to that point, the point where this dashed line intersects that plane. And then the angle measured from the x-axis, that's phi. Okay? R, theta, and phi. And of course, there are relationships between the Cartesian and the polar coordinates. For example, r, the distance from the origin, is clearly the square root of x squared plus y squared plus z squared from the Pythagorean theorem. And trigonometry shows us that z can be written as r times cosine theta. X can be written as r times sine theta times cosine of phi, or phi, and y can be written as r times, sine of theta, sine of phi. Okay? All right. And once we've set up our coordinates, then it's straightforward, at least in principle, to write down Schrodinger's equation in these new coordinates. All right? So Schrodinger's equation, which previously looked like this, well, it contained this term, del squared psi, as second derivative with respect to x of psi plus second derivative with respect to y of psi and second derivative with respect to z of psi. Now we're going to write it in spherical polar coordinates. And finding the new form would basically just be going through this equation and substituting the polar coordinates for the Cartesian coordinates using the rules that we just wrote down. And I'll tell you, if you ever have to do this, as I believe I had to do it once, it's kind of a mess. All right? In fact, the formula that we get looks a little bit uglier than the one that we just wrote down for Cartesian coordinates. Here, I'm going to show you what it looks like, and then we'll go on. But I'm not going to derive it. We won't have to do that in this course. Okay, switching over to some PowerPoint slides now. Schrodinger's equation in spherical polar coordinates looks like this. And I guarantee you, all we've done here is to switch from Cartesian coordinates to polar coordinates and just turn the crank. So we have minus h bar squared on the left-hand side, minus h bar squared over 2m times quantity, second derivative with respect to r squared, plus 2 over r times the first derivative with respect to r, plus 1 over r squared times the quantity, d by d theta squared, plus cotangent theta, d by d theta, plus cosecant squared of theta times second derivative with respect to phi squared of the wave function. And that's equal to E minus U of R times the wave function again. So this whole thing on the left-hand side that's just del squared written in spherical polar. All right? Well, kind of a mess. All right? Now, when we look at problems that have spherical symmetry, it turns out that we can always find energy states that are separable solutions. That is, we can find energy states where the wave function is the product of one function that depends only on r, we'll call it capital R of r, times another function that depends only on theta, we'll call that capital theta of theta, I guess, and the third function that depends only on phi. Okay? And if we substitute this separable solution back into Schrodinger's equation and turn the crank, doesn't sound like much fun, but it's not so bad. Then what we'll find is that Schrodinger's equation breaks up into three simple ordinary differential equations, much like what we did in Cartesian coordinates last time, only a little bit messier. And now we're going to take a look at these three equations. Okay? The first equation is an equation for the phi function, capital Phi of phi. And that differential equation looks very simple. Second derivative of capital Phi with respect to phi, it turns out to be minus m squared times phi. All right? And this is a simple enough equation that you can probably tell that the solutions to this are, well, we could write them as sine and cosine functions. That would be fine. Or we could write them as complex exponentials, like e to the plus or minus I times m times phi. And that's what we're going to choose to do. Okay? Now, something interesting, since since the wave function has to be single valued, we know something about capital Phi of phi. We know if we start tracing out the wave function and we go all the way around from phi equals 0 to phi equals 2 pi, that when we get back, we have to get back to the same value, right? The wave function has to be continuous at every point. And because of that, that means that capital Phi of 2 pi plus the angle has to be equal to phi of the angle. That's the condition for the wave function to be single valued. Okay? And the only way that that can be true is if m here is an integer. And so m is an integer, and it can take on values 0, 1, 2, 3, 4. Actually, it's common to absorb this plus or minus in our solution to allow m to be 0 plus or minus 1, plus or minus 2, plus or minus 3, and so forth. Okay? M here is our first quantum number for the central force problem. All right? So separation of variables breaks up Schrodinger's equation into three ordinary differential equations. The first of these is the equation for the phi function, and we've just taken a look at that. It's straightforward. The second equation looks like this. It's not as easy to parse, all right? Minus, well, here we are. We have second derivative of the theta function with respect to theta plus cotangent of theta times the first derivative of the theta function with respect to theta equals minus m squared times secant of theta, the coordinate, times the theta function. All of that turns out to be equal to minus L times L plus 1 times the theta function. Yikes. Well, this looks like a difficult differential equation for us, but it turns out that one can show that this is equal to a very standard differential equation, and to which the solutions are well known. They're not well known to us, maybe. They don't just jump into your mind, but they turn out to be a set of functions called the associated Legendre polynomials. And these are a set of functions that are familiar to applied mathematicians. They're tabulated in Mathematica, and they're pretty well known. They just might be new to us. Okay? Um, in general, the associated Legendre polynomials are given here, at least the first few are, excuse me. And here they're written as P of x, where x here can take on values between minus 1 to plus 1. Okay, that's the range of these polynomials. And you can see that the first polynomial is just a constant. The second is a linear function, that's P01. The third looks like a linear, is actually a linear function as well, but it has a different form. The fourth is, the next ones are quadratic functions, and there are three of them here. Okay? You'll notice that the associated Legendre polynomials, there are two quantum numbers that go into these solutions. There's m, which we've already talked about, and then there's a second quantum number, L. In this solution, in this general solution here, we have the form of the function depends on both m and on L. And then instead of being written as p of x, the argument turns out to be cosine of theta. So it's p ml of cosine theta. Okay? Still, it's quite a jump, right, to see these things. In fact, the very standard notation is to combine the theta function and the phi function and put them together into one combined thing, which we call the spherical harmonic function. Okay? So the spherical harmonic functions are just products of the theta functions and the phi functions. Okay? And well, these are kind of interesting. You know how if we have a stretched string and we pluck it, we know that whatever vibration we see, we can decompose it into sine and cosine waves, okay? Subject to the boundary condition that the end of the string remain fixed. So for linear systems, the important functions are sine and cosine functions, right? The different standing waves on our string are sinusoidal functions. Well, now imagine a system that looks like a spherical drum, okay? So a spherical drum, and we strike it so that the sphere starts to vibrate. Well, the sphere can vibrate in many different ways, and you can decompose those uh, um, standing waves into spherical harmonics. So the spherical harmonics are the functions that would describe the vibrations of a spherical membrane that's been disturbed. Okay? Well, um, that's what these are. And now we'd like to take a look at some of these, okay? And as I show them to you, I think you're going to find that they actually look familiar. Okay? So these are tabulated in the book, and that's what I'm showing you as a table from there. And I'm also going to show you some polar plots that show how the amplitude of these functions depends on angle. Here, the first spherical harmonic function is y00. That means m equals 0 and L equals 0. Okay? And you can see that it's just a constant. If we make a polar plot of this function, we're plotting the amplitude as a function of angle. And in these polar plots, the amplitude is represented as the distance from the origin, and then the angle is just the angle. So the polar plot of a constant function just looks like a sphere. All right? So that's y00, the lowest spherical harmonic. Here, let's look at the next one. The next one is y m equals 0, L equals 1. All right? And this looks like a different constant times cosine theta. All right? If I make a polar plot of this, well, it looks like a plot of cosine theta. That is, at angle 0, at polar angle 0, the function has its maximum value, it's plus 1. As the polar angle gets bigger and bigger, the value gets smaller and smaller and smaller until here, at theta equals 90 degrees, the value would be 0 because cosine of theta is 0. As we go to from 90 to 180 degrees, the magnitude will get bigger and bigger and finally reach 1. But now the sign will be negative instead of positive. Okay? In this plot, we represent the sign, or more generally, the phase, with the color. So blue represents positive amplitude, and red represents negative amplitude. Okay? Of course, a wave can be have positive or negative amplitude at every location. All right. So that was y00. But I'm sorry, 0, 1. Y01. But we could have y with L equals 1 and m equals 1, or L equals 1, m equals negative 1. And those two functions are shown here. They're very similar. They have a constant value times sine of theta times another function that depends on phi. It's actually e to the plus or minus I phi. Okay? And that's represented here. So in this case, the amplitude at polar angle theta equals 0 is 0. And then as the polar angle increases, the magnitude increases until we reach 1. And then as we go to larger and larger angle, it goes back to 0. Okay? If we think of how this function depends on theta as well as phi, well, it looks kind of like this donut here. In this donut, the color represents the phase of this complex number. Sorry. Okay? And so it starts at red, which would mean phase equals 0, so the quantity would be positive 1. And then it goes, as you go around, you go through a web of colors to the other side. well, I guess it starts which at blue, which is a positive one, and then goes through to to negative one through all the complex values. In any event, um, the color represents the value of the phase of the wave function. All right, here's the next one. Y2, 0. L equals 2, M equals 0. And this looks like this. Of course, this one varies like 3 cosine squared of theta minus 1. So when theta is equal to 0, this is equal to 3 minus 1, or 2, and it's positive. And then as the polar angle increases, the function goes to 0, and then it becomes negative. So when theta is equal to um, 90 degrees, of course, this function is 0 minus 1, so it's negative. And then as we go to larger angles, it becomes positive again. Okay? And this function's independent of phi. And then we can go through and look at several other cases. So this is y equals 2, um, I'm sorry, L equals 2, M equals plus or minus 1, L equals 2 plus or minus 2. And they're shown here. All right, let's stop for a second. So those are the first few spherical harmonics. Okay? It's a big jump to talking about these, but as you look at these, I wonder if they don't look familiar to you. At least all of us who've taken who've taken some chemistry, maybe even in chemistry in high school, have seen sketches of atomic orbitals, right? And I bet if you look carefully, these look a lot like atomic orbitals. All right. And they do. And it's not a coincidence. And we'll see why in a few minutes. Okay? But in fact, the shapes of the spherical harmonics are just the shapes of the atomic orbitals. All right, I think we'll stop this video here, and then we'll continue to talk about angular momentum in the next one. Hang on.